In the last few lectures, I've told the story of how huge structures have grown in the universe as it's aged, the birth of the first stars, the maturation of galaxies, and the development of the galaxy web. Our focus couldn't have been further from our cosy home here on Earth. But surely an important part of any creation story is how our own very local world came into being, including, and perhaps most importantly, how we ourselves came to be here. What does modern cosmology have to say about this? Does it deal with such mundane things as this podium, or my pen, or even my hand? Does it tell their story? The answer is yes, of course, it must do. We are no less a part of the universe than any star or galaxy, and we can only have arrived here via a cosmological route. So it's this route I want to explore in the next 3 lectures. And I hope by the end of them, you will look differently at everything around you, and you may even feel your own cosmic origins. So let's start by carefully looking at my hand. What's it made from? As you probably know, if we zoom ever deeper down in scale, we first pass skin, then cells, then organelles within those cells, then giant molecules, and finally, about 8 factors of 10 in magnification, we arrive at an ocean of tiny jostling spheres. These are the atoms from which everything is made, and they are famously tiny compared to us. If this marble were the size of an atom, then my hand would be the size of the Earth. Imagine fingers 5,000 miles long, 1,000 miles across, packed with marbles. Atoms are incredibly tiny, and they're incredibly numerous. Now, as you probably know, there are about 100 different kinds of atoms, which differ in weight and size and how they stick to each other. The most famous way to organise them all is in the periodic table of the elements, something I suspect you learned about in high school. Each element is made from atoms of just one kind, and they are all arranged in a sequence from 1 to about 100 that wraps around so that elements with similar chemical properties all line up in columns. Here are just 4 examples. Lithium and carbon are numbers 3 and 6. Gold and uranium are numbers 79 and 92. Of course, it's the amazing ability of atoms to stick together as molecules that makes atomic matter so creative. In the same way that a few dozen letters in an alphabet can make millions of words that can be arranged into sentences and books and libraries, so a few dozen kinds of atoms can make millions of molecules that can be arranged into cells and organs and people. Here are some models of simple molecules: water, ethanol, the neurotransmitter serotonin, and a tiny fragment of DNA. Now, since our aim is to learn how atoms were made, we need to get beyond this simple cartoon of atoms as shiny coloured spheres. So here's a slightly better diagram of a beryllium atom. That's number 4 in the series. There are 4 lightweight, negatively charged electrons orbiting around a heavy, positively charged nucleus. It's the electric force of attraction that keeps the electrons in orbit, rather like the sun's gravity keeps the planets in orbit. Now, the atom's nucleus appears way too big in this diagram. It's actually 100,000 times smaller than the atom. A fly in the middle of a football stadium is a good match to a nucleus in the middle of an atom. So, if you remove the space from all the atoms in all the people of the world, we would all fit into this sugar cube. You see, relative to nuclei, atoms are very large, very empty things. Now, despite their amazing tininess, we actually know a great deal about atomic nuclei. They contain two kinds of particles, protons and neutrons, and it's the number of protons that defines the element. 1 for hydrogen, 2 for helium, 79 for gold, and so on. Usually, there are slightly more neutrons than protons. So, for example, gold has 79 protons, and it has 118 neutrons. Now, the neutrons and protons are held together very tightly by a second kind of force called the strong force. But unlike the electric force, it has a very short range. You can think of it a bit like Velcro. Close enough, it sticks. But a little further, nothing. Now, this attractive Velcro force is crucial because without it, the positively charged protons, which repel each other, would just blow the nucleus apart. Now, at this point, I want to introduce one of the most important graphs in astrophysics. It's called the nuclear binding energy curve. Along the bottom, from left to right, we have all the elements from 1 to 92. And up the y-axis, we have all the energy that holds all the protons and neutrons together. It's called the binding energy. It's the energy you would need to pull the protons and neutrons apart. The lower a nucleus sits on this curve, the more glue energy there is, the more tightly bound it is. Notice that the curve starts very high with hydrogen, drops to a minimum, and then slowly rises again. Now, the reason it has this shape is because there are both attractive and repulsive forces at work inside the nucleus. For lighter nuclei, with not too many protons, the proton repulsion isn't that much. So the strong, attractive Velcro force dominates and makes nice, tightly bound, small nuclei. But as we move to the right, the proton repulsion begins to build up and competes with the attractive Velcro force, so the curve begins to rise. And really big nuclei, like uranium, are fairly close to just blowing themselves apart. The element that sits at the bottom of this curve is iron, number 26. Its nucleus is the most tightly bound. Okay, well, now imagine the following. Let's take two light nuclei and fuse them to make a single heavier nucleus. For example, let's fuse hydrogen to make helium. We move to the right and downwards on this graph. Since lower on the graph is more tightly bound, then energy is released. Think of rolling a ball downhill. So fusion reactions that combine light nuclei together release energy. It's these kinds of reactions that power stars and also hydrogen bombs. Now look to the right. If we break apart a heavy nucleus like uranium, we move to the left on the curve, which is also downhill. So energy is also released. These are fission reactions, and they power nuclear reactors and also atomic bombs. Now, what's not so apparent from this particular graph is that the actual amount of energy released in nuclear reactions is about 1,000,000 times greater than in chemical reactions. For example, fusing a kilogram of hydrogen to make helium releases about 1,000,000 times more energy than burning a kilogram of coal to make carbon dioxide. Of course, burning coal is easy, but fusing nuclei is difficult. Why is that? It's because nuclei are all positively charged, so they repel each other like crazy, and it's very difficult to get them together. One way to do this is to rely on very high temperatures to hurl nuclei together, such that they can actually collide and stick. The speeds need to be very high, typically a few thousand kilometers per second, corresponding to temperatures of millions or even billions of degrees. These kind of reactions are called thermonuclear fusion because they rely on high temperatures to get them going. Now, it's these thermonuclear reactions that provide the crucial link to the nature of stars. You see, the reason stars, like the Sun, are hot, luminous balls of gas is that they are busy converting light nuclei into heavier ones, and the energy released keeps the star hot and shining. Ultimately, then, new elements are built up inside stars, and that overall process is called nucleosynthesis, the synthesis of atomic nuclei. The bottom line is, stars are atom factories. So let's look in a bit more detail now at how all of this actually happens. Here's a star. It happens to be the Sun, but it's going to represent stars in general. Let's cut into it to see its interior. Stars, of course, are huge things with huge quantities of matter, whose enormous weight compresses the interior to make an extremely dense, hot core. At the centre of the Sun, for example, the gas is 10 times denser than lead and 14 million degrees. Now, these conditions are ripe for thermonuclear fusion. In a very real sense, the core of a star is like a furnace, and the rest of the star is like an insulating jacket. Within the furnace, a fuel of lightweight nuclei is being burned in the nuclear fusion sense to make an ash of heavier nuclei, and that burning gives off energy, heat. Just like a normal furnace, the heat generated from the burning does two things. It keeps the core hot so that the burning can continue, and it also moves out through the insulating jacket, and ultimately it escapes into the colder environment. Now, in the case of the Sun, the energy makes its way out of the star in a couple of ways. X-rays slowly diffuse up through the foggy interior, and huge convection currents carry hot gas from below up to the surface. The surface is really the part of the star where the gas turns transparent, so that the light from the hot glowing gas is set free and streams out into the darkness of space. So when you next look at those points of light in the night sky, try to think of them as glowing surfaces of distant atom factories. They're a direct indication that new atomic nuclei are being made. Now, there is a key property of stellar furnaces that you won't find in normal human furnaces. The nuclear ash from one thermonuclear reaction can become the nuclear fuel for another thermonuclear reaction. Let's go back to our binding energy curve. The first thermonuclear reaction fuses hydrogen to make helium. But when all the hydrogen fuel runs out, helium nuclei can fuse to make carbon and oxygen. And when the helium runs out, the carbon and oxygen nuclei can begin to combine to make neon and sodium, and so on and so on. The nuclear ash from one reaction becomes the fuel for the next, and this sequence steadily creates heavier and heavier elements. But there are two catches to this simple story. First, it only works up to iron, which sits at the bottom of the binding energy curve. It's the ultimate nuclear ash, because to go beyond it is uphill, which of course absorbs energy, not releases it. The second catch is that these later reactions need much higher furnace temperatures, for the very simple reason that heavier nuclei have more protons, so they repel each other even more forcefully. So you need even higher temperatures to get the nuclei together. For example, hydrogen fuses at 15 million degrees. Helium fuses at 100 million degrees. Carbon fuses at 600 million. And oxygen fuses at 1.5 billion degrees. Now, whether or not a star can actually achieve such high furnace temperatures depends on the mass of the star. You see, when one fuel runs out, the core of the star, that's the furnace, begins to contract under its own weight, and this compresses the core and heats it up. Now, how hot the core gets depends on how massive it is. Relatively low-mass stars, like the Sun, can never ignite carbon, while intermediate-mass stars can never ignite neon. It's only massive stars that can fuse elements all the way up to iron. Now, I'm going to talk about these reactions in more detail in next lecture, including the all-important processes that make elements beyond iron. But for now, let's just recognize that the furnaces that reside deep inside stars can generate the whole sequence of atomic nuclei that we find in the periodic table of the elements. Now, it's all very well making atomic nuclei deep inside stars, but here they are in you and me. How did they get from out there to in here? Let me trace that remarkable journey for you now. For many atoms, the process starts with what's called convective dredge-up. They are brought up to the surface in huge hot currents of gas. Of course, higher up in the star, the temperature is lower, and so one by one, negatively charged electrons get caught and attached to the positively charged nuclei. And by this time the atom arrives at the surface, it's all but one or two of its final quota of electrons. So, while nuclei are built in the star's core, atoms are assembled near the star's surface. The factory has, if you like, its conveyor belt. But we still need to get the atoms out of the star and into you and me. And that takes quite some doing. Ultimately, what happens is that the atoms are ejected into space when the star dies. And I'm using the term die more or less as you would for a furnace, when the fuel finally runs out and the thermonuclear reactions cease. Now, there are actually several ways in which stars die, and I'm going to mention 3 of them. So let's start with stars like the Sun, what astronomers think of as relatively low-mass stars. About 5 billion years from now, when the Sun's fuel begins to run out, its core will begin to contract. And fusion reactions just outside the core begin to burn extremely vigorously and create lots and lots of energy. And this makes the Sun swell up enormously. Here's the Sun today, sitting at the center of the orbits of Mercury, Venus, and Earth. But as its furnace begins to die, the Sun will expand to engulf the orbits of Mercury and Venus and almost touch the Earth. It becomes what astronomers call a red giant star. Needless to say, at this time the Earth's surface will return to an utterly barren and lifeless state. Now, with its atmosphere so extended, a star's gravity can't easily hold on to the outer layers, and as more and more energy comes up from below, it actually pushes off the star's outer atmosphere. And over a few tens of thousands of years, the outer layers are blown away in a strong wind, and a beautiful nebula is created. Now, the atoms in these nebulae steadily move out to join the rest of the material between the stars, and I'll return to pick up their story in just a minute. But first, notice that in the middle of many of these nebulae, you can see the exposed, hot, dead core. These hot cores are called white dwarf stars. They're made of highly compressed carbon and oxygen, not much bigger than the Earth, but with about as much mass as the Sun, so they're incredibly dense. Now, normally, over billions of years, they would just gradually cool down and fade away. But in certain special circumstances, they can be rekindled in a very dramatic way as a supernova explosion. This can happen when the white dwarf happens to be in a binary star system with a second companion star orbiting nearby. When the second star begins to exhaust its hydrogen and swells up, some of its outer atmosphere falls over onto the white dwarf. As mass is transferred, the white dwarf gets compressed and heated, and there is a critical moment when its temperature is sufficiently high that the carbon and oxygen nuclei undergo thermonuclear detonation, and the entire star explodes. We actually met this kind of supernova back in Lecture 6 because they provide a fabulous way to measure the distance to very remote galaxies. But in the current context, we're more interested in the fact that thermonuclear detonation not only creates a whole set of heavy elements, mainly around iron in the periodic table, but it also hurls them out into space at thousands of kilometers per second. Now, there is in fact another type of supernova that comes from the death of a much more massive star, whose furnace can actually ignite elements well beyond carbon. This time, when the fuel begins to run out, these massive stars swell up even larger than red giants to become what are called red supergiant stars, roughly the size of Jupiter's orbit. But way down in the center sits an amazingly dense, hot core. See, with such high temperature and density, elements heavier than carbon start fusing so readily that they form a set of nested concentric shells. Many furnaces burning simultaneously, each receiving fuel from the shell above and dumping its nuclear ash to the shell below. Right at the heart of this is a dense sphere of iron nuclei, the ultimate nuclear ash that cannot yield any more fusion energy. It's about the size of the Earth, but with more than the mass of the Sun. As time passes, this iron core steadily grows in mass, and in one of the most remarkable events in astrophysics, the pressure supporting this iron core snaps, and in a fraction of a second, it collapses and triggers a monumental explosion. Just to give you an idea of the energy released, if we orbited such a star and were subjected to its explosion, each square foot of the Earth's surface would be hit by the energy equivalent of 1,000 times the global total stockpile of nuclear weapons. That's each square foot. These core collapse supernovae are prodigious astrophysical bombs. But in the current context, they're also remarkably creative. They make elements past iron all the way up to uranium, and furthermore, they hurl these new elements out into the interstellar medium. The spreading guts of these stars' explosions is called a supernova remnant. In that animation, the remnant was designed to look like the Crab Nebula, whose star exploded almost 1,000 years ago. Here are two other young remnants that are about 400 years old, and they've now expanded to be just a few light years across. And they're found to contain almost pure heavy elements with little or no hydrogen or helium, which is a pretty strong indication that these elements were indeed made inside these stars. Now, after many thousands of years, like these older supernova remnants, the gas has expanded to cover several hundred light years. And in time, it gradually disperses and joins what astronomers call the interstellar medium, the tenuous gas that exists between the stars. This is the next stage in the lives of our atoms. So let's take a closer look at it now. You can get a reasonable impression of the interstellar medium in this lovely wide-angle image of the Milky Way. All that patchiness is gas and dust between the stars. The gas is exceedingly thin, maybe 1 atom per cubic centimetre. That's equivalent to 1 person per continent for humans. In addition to single atoms, there are also groups of maybe 1 million atoms stuck together in tiny grains that astronomers call dust, though you can think of them as very fine smog particles. In fact, those dark patches you can see across the Milky Way are caused by this interstellar smog, blocking the light from more distant stars. You see, you can view the interstellar medium as the galaxy's highly polluted atmosphere, polluted by all the heavy elements and smog particles coming from all those atom factories, the stars. They really are filthy furnaces. After 14 billion years of pollution, the Milky Way's atmosphere contains about 2% heavy elements. If you compressed the gas to match our own atmosphere's density, you could not see your hand in front of your face. It is that polluted. Of course, one can choose a more positive metaphor and say that the interstellar medium is enriched by heavy elements. After all, they're an essential ingredient of building planets and people. So let's follow our story further. How do these atoms continue their journey into the Earth and into you and me? Well, our atoms probably drifted around in the interstellar medium for at least 1 billion or 2 years, subject to the general mixing of galactic rotation. And in time, at least some of the atoms find themselves in denser clouds like this. When gas is gathered into denser regions, gravity begins to take over. And in small pockets, it can cause a headlong collapse that ends in the formation of a star and its planets. Basically, these utterly beautiful sites are where new stars are born. Here's a lovely example, the Great Nebula in Orion. If we zoom into the region with the Hubble telescope's sharp vision, we can find new stars forming all over the place. Perhaps a few thousand will ultimately form. But more important for our current story is that these new stars are surrounded by a flattened disk of gas and dust, and it's within this disk that planets form. As this artist's painting suggests, conditions in the disk allow gentle collisions to build larger structures. So atoms stick to form grains, grains form pebbles, pebbles form boulders, and at some point gravity takes over and attraction onto the largest boulders builds first embryonic planets and eventually full-scale planets. In the case of the Earth, about 10 to the 50 atoms ended up in a spherical ball, looking maybe a little like this, with a barren, crater-pocked, sterile surface heaving with volcanism. In one of the most remarkable transformations of all, over a period of 4.5 billion years, this young, sterile planet gradually turned into our current world, with warm oceans filled with fish and continents teeming with plants and animals. That transformation has its own wonderful story and is, of course, way beyond the scope of these lectures. It has its roots in the amazing ability of atoms to bind together in a myriad of complex ways. At glacial pace, an extraordinary selection process begins to leave its mark. Molecules that are stable and can duplicate gradually become more common, and this principle continues in a hierarchy of structures that ultimately leads to life. Natural selection and the passage of time are superb craftsmen. With unimaginable dexterity, instructions inherited from long lines of ancestors coax billions of atoms into huge structures. After thousands of millions of years, it's even possible for atoms to arrange themselves into plants and animals and people. And that brings this lecture full cycle. We set out to track our own matter's history, to find its location in the cosmological story. And what a story it's turned out to be. Our atoms were forged billions of years ago, deep in the fiery furnaces of ancient stars long since dead. When those stars died, the newborn atoms were launched out into the cold emptiness of interstellar space, where they drifted for several billion years. In time, they joined a dense, collapsing cloud and became incorporated into the sun and planets. A select few ended up on the Earth's surface and spent time moving from plant to animal to soil and back again. And for just a brief moment in their long, long lives, billions have gathered to make your body. And some of these are, right now, comprehending this sentence. And in a sense, they're actually thinking about themselves.